Hello, everyone. We're back here at Azure channel with Fernando, Rolnik, and Raul Rai to record something a little bit different. We did the STU series. Now we're going to talk about dynamic admission controller on AKS, but we're going to use Azure Functions for that. Raul, Fernando, welcome.
Hi
Hi,
everyone.
everyone. Hi, George. How are you?
Hi.
So let's start.
Let's start. I think it's a good thing. Before, don't forget to subscribe the channel. I'm going to be publishing many videos in the next few weeks, and please subscribe the channel.
And
Raul,
activate the notifications to get notified when we publish new
for
videos.
sure, for sure. How are you going to use Azure Functions for admission controllers on Azure Kubernetes Service, Raul? Go ahead. I want to see that.
Thank you. So I will start with the use case first, why we need admission control and where does it sit in your Kubernetes API server. And then we'll talk about how you can extend the existing admission control and make it serverless, which is quite interesting. So Kubernetes admission controller is a small piece of code that sits in your Kubernetes API server. And whenever you send any requests to the API server in order to create or modify a Kubernetes object, for example, let's say you want to create a new pod in your service, or you want to, for scaling out a service or scaling down a service, or you want to create or delete a service, this particular piece of code would receive all the requests, and it would decide whether that request should be approved, as in it should be submitted to the HCD storage in order for it to be provisioned by Kubernetes, or whether it should discard the request. So you might already have used this functionality a bit, even without realizing it. For example, if let's say you instruct Kubernetes to create a service in a namespace that doesn't already exist, you would notice that you would immediately receive feedback from the API server, and you can see that response in your terminal saying that you can't create a resource in a namespace that doesn't already exist. So that particular admission controller is called Namespace Access, and that is responsible for discarding your request, other than rejecting the request that you make to it. But this model is very flexible, as you can imagine. So this controller doesn't handle all the requests by itself, although it does have certain of these admission controls in itself. For example, namespace access is one such control. But you can extend it so that it can talk to other services in order to accept or deny a request. That brings me on to another aspect of the admission controller. So admission controller are of two types. One is mutating admission controller, and another one is validating admission controller. So what I had been speaking of till now is the validation admission controller, the piece of code that is responsible for either accepting or rejecting your request for creating or updating a Kubernetes object. Another family is this of controllers is this mutating admission controller, which can modify your service request and the Kubernetes request before processing them forward. So if you have ever deployed things like Nginx on your cluster or Istio on your cluster, that's where these mutating admission controllers come into picture. So you must have seen that in the Istio series, we spoke about this, that if you want to inject a sidecar to your deployment, to the pods that get created, you simply add a certain label in your spec, and it is read by Istio, which in turn injects a sidecar to your pods. So how Istio does it is through a mutating admission controller. So when you submit a request, an STO mutating admission controller would intercept the request. I'm talking about a request to create a pod here. And what it would do is it would modify that request and add another container to the pod, and also modify the networking capabilities in your container. And then finally, a spec which is very different from the original spec is submitted to Kubernetes for provisioning. And that's how those sidecars get injected in your in the pods that you request to be created. So now that we know what these two families of admission controllers are, I would like to take you through the steps involved whenever you submit a request to API server and how it is stored to Hcd. I have spoken about objects getting stored in Hcd about 2 or 3 times now. I will briefly tell you how Hcd works. So Kubernetes is an eventually consistent system, which means that whatever requests you submit, they are not provisioned at the very same instant. So it's not a request response based system where you ask Kubernetes to create a pod and it is by the time the request returns, a pod is created, although it may seem so because things happen very fast. What happens is that when you submit a request, they are persisted to a store. Generally, it is Hcd and AKS. You can also replace Hcd with Cosmos DB. But what the role of this store is that whatever requests you submit, they are persisted there. And then there are a bunch of watchers which always keep looking for the resources, the data that gets stored in this Hcd. And they pick those requests up and then do their job. So there is a watcher for creating a pod, watcher for creating a namespace, things like that. And they will pick up those requests and try to make the state of Kubernetes consistent with what you have requested. So all we need to do is to validate whether the request that is going on to Hcd is a valid one, and then let Kubernetes worry about the rest of the process. So what I'm going to show you here is the path that every request takes in order to reach Hcd. So on the left, this tiny icon, let's assume it's a request to create a pod. So as soon as this request is submitted, it first gets authenticated and authorized whether the person with the right set of permissions is making those requests. Once the request has been authenticated and authorized, they move on to the mutating admission controller. So as we already discussed, that mutating admission controller can modify the spec and inject, let's say, a sidecar or make any changes to the spec. Also, what it can do is it doesn't need to process everything within the code base itself. It can defer the job of mutating the spec to another system, to another service. And this service can either live within the cluster or it can live outside the cluster as well. So what it does is it sends an admission review request to a service. And what it expects from the service is an admission response. And the admission response would essentially contain a modified spec, which might contain things like sidecars in it. So once the schema has been modified, it goes on for validation. So Kubernetes understands a handful of schemas by default, for example, pod services, those sorts of things. So the schema is validated. And afterwards, the other family of admission controllers kick in, which is the validating admission controller, which would validate whether the request that has been mutated, or in the other cases where you don't make any modifications to the spec, they just flow all the way over to the validating admission controller. It validates whether the request should be processed by Kubernetes or not. In order to do that, it follows a similar model to mutating admission controller, wherein it can send a request to an in-cluster hosted or externally hosted webhook, and it would expect admission response back from it. So in both the mutating admission controller and validating admission controller, you would notice that the schema of requests and response are the same. So once a deployment has been validated, it is sent on to Hcd for storage. From there on, Kubernetes would take care of the rest of the process. So I spoke about the request and response schema in the Kubernetes API server pipeline. Let's look at what the actual schema is of a review request and a review response. So on the right is the admission review request, which Kubernetes sends to a webhook, which can again be hosted inside the cluster or outside the cluster itself. And that is the schema of the request that is sent. The most important thing to notice about the schema is that the spec that you apply, you kind of get the whole copy of that spec in the request itself. So you can do things like checking whether labels are in place and tags are there. So those kind of checks can be made. And for mutation purposes, you can modify the spec that is sent as part of this request. Use that spec, modify it, and send it back. On the left-hand side is the response that the webhook should return. So this response is again of kind admission review. So this is quite interesting that the kind in both the cases are the same. And how the request and response are versioned is through a UID. So on the right, you can see that there is a UID field with a correlation ID in it. The response should send the same UID. The only thing that determines, so here we are going to talk more specifically about validating webhooks. So the only thing that determines whether a request, an object should be provisioned or not, or whether this request should be allowed or not within the Kubernetes cluster is this property. If its value is set to true, then the request moves on and it gets provisioned in your cluster by us storing it in Hcd cluster. Not us, but rather Kubernetes that is going to store this request in Hcd, and from where on it will get provisioned. If you set it to false, then this request will be discarded. So this is a very basic architecture of how you can write a custom validating webhook, which lives out of the Kubernetes API, outside of your Kubernetes server. And here you can see that a developer can submit a request to Kubernetes API server, and through the webhook that we saw in the pipeline earlier, the API server can forward that request onto Azure Function, and the function would need to return a response back to API server with whether the policies that are written in the function accept or reject a certain deployment, and those details are sent back to the developer. One of the good things about function is that it has support for tons of bindings. And I was just watching the Ignite conference, and Azure Functions are now enabled to use more than 300 bindings now. Writing code for a lot of them could be very tedious. So you can use the native Azure Function bindings in order to talk to many external services. So I am trying to demonstrate that by using the native Twilio binding of Azure Function, so that after accepting or rejecting our deployment, Azure Function can notify the ops or SRE team that whether a deployment has been submitted to the API server or whether it was rejected because of some reason. So in a way, you can keep operations and SRE team in loop on whatever happens in your API server. So there is a catch to it when it comes to AKS. So I'll talk about that next. So the Kubernetes API server in AKS can't talk to services hosted outside the cluster directly. So the API server is actually a part of the control plane in AKS that is managed by Azure, and you just need to worry about your workloads. So the managed this managed plane, which is the control plane of Kubernetes, can only speak to the nodes that are part of your cluster. So in order to achieve the same functionality, what we would need to do is first forward the request onto a service that can in turn send the request onto an Azure function. So that's where this reverse proxy comes in. So I wrote a small reverse proxy using Golang, which sits in the cluster as a service. So whenever a new deployment is submitted, the API server would first forward the request onto the reverse proxy, and the reverse proxy forwards the request as it is to an Azure function, and the rest of the workflow is still the same. So what you see on the screen right now is a validating webhook. So in this particular configuration that you see, you can make a request. You can configure a URL to which Kubernetes API server should forward the request in order to get a deployment validated or rejected. And the URL property that you see here is that of the function in our case. So the Azure function that will either accept or decline the request. And in the rules section, you specify what all conditions, if they hold true, would the request be forwarded to the Azure function. So here you can see that I have specified that any deployments that get created within a namespace. So the deployment shouldn't be created in the default namespace. That's what it means. So if the deployments are either created or updated, then they should be then such requests should be forwarded on to the Azure function in order for validation to happen. When we bring in the reverse proxy into the mix, then this configuration gets altered slightly, and we'll look at that configuration in our demo. So instead of specifying the URL to the function, you actually specify the service which lives within your cluster to which the request should be forwarded before, so that it can process it. And is the service that is relied to for accepting or rejecting a certain deployment. So we'll move on to the demo. Sorry.
Before start the demo, is that timeout something we can increase there? Like what I'm asking, if your Azure functions take longer for some reason, then you're doing more validations, you're talking with maybe some like company systems, and that's going to take more than 30 seconds. Can you increase that? How that works?
All right. So regarding timeout policy, 30 seconds is the maximum amount of time till which this request can wait, because validating webhooks are executed within the request flow. So they're not asynchronous requests. So once a request comes in to the API server, it is held within the API server until validating webhook returns either accepts or rejects a deployment. So it can be used only in scenarios where your decision making is automated. So for instance, if you require manual approval, it's much better to do those kind of things in your CI/CD pipeline. And here you can check for things like whether the image has been let's say run against a security scan, or for example, in this scenario, if you want to notify someone whenever a a deployment occurs in your system, or even for other kinds of scenarios where you want to let's say block deployments within your cluster between a certain date. Let's say you don't want to deploy anything, any new service in your cluster between, let's say, Christmas and New Year. Whereas you might want to have patching done on your existing services within the same period, then you can enforce those kind of constraints. They're very dynamic constraints. You can enforce them using these dynamic validating webhooks.
Okay, that's a good point, because with Azure Policy becoming GA now on AKS, we don't have these customized policies, but you still have some building that we can use. But these will be like a complement thing where you can do extra things that's not possible using maybe Azure Policy. Then depends of your scenario, be I think many possibilities that you can use that. That's great.
Yes, exactly. So that's what my recommendation also is, to use Azure policies for any scenarios that are that you might have, which requires static analysis of your deployments. For example, checking for things like whether certain labels exist in your service, or even for, let's say, whether the namespace meets a certain criteria. So those kind of things are already baked into Azure policy, and those are what should be used. And this should be used when you have some dynamic constraints to take care of that are not yet supported by Azure policy. So you can use your own custom rules and put them in a validating webhook configuration as a validating webhook, and it would work just like Azure policy does. So to talk about this in detail, what I'm going to show you today, I've documented that in my blog, and this blog post would also be available on Azure Tower, and you can refer to either of the two places and get to know about Azure policy or this demo in detail. So what I'm going to do right now is walk you through first the Azure function, and then I'll talk to you about the proxy that I built. This is a very simple function. So all it does is it accepts an HTTP post request, and it has just one rule baked in it, which is to reject any deployment if it has less than 2 replicas in it. And if there are, yeah, that's the only rule that I have for it. So let's look at the body of the function. So here you can see that this is the signature of the function. I have let this function stay anonymous, but there's nothing really stopping you from making it more secure by adding keys to it. So you can have function level authentication and authorization, so that it's not that anyone can simply invoke this function and charge your account for it. And you can see that there is a Twilio SMS binding in it. And using this binding, I would be able to send SMS to my phone, which I have configured for now. I created a trial account with Twilio, and that's what I use for this demo. So looking at the code, the first thing that it does is it reads the body of the request, and it deserializes that request into a dynamic object. And from here, I can see whether the operation that was requested is create or update operation. Later, I try to find the name of the application from here. And then what I do is I run this very simple rule on how many replicas have been requested to be provisioned for a certain deployment. And if the replica count is less than 3, then I send an error message back to the ops and SRE team. By message, I mean SMS. And I also send a message back to the developer requesting this request to be provisioned by sending an admission review response back. So as I said that the response needs the UID of the request in order to control for which request this response was returned. False means that this request won't be processed any further and that this request is not valid. And the third part of the body is the message that would be displayed on the terminal, which would say that replica count should be greater than 2. So another thing that I do here is that I extract the containers that this particular request has requested to be created. And if the operation is create, then it again dispatches a message to the ops SRE team listing all the containers that are going to get created as part of this deployment. Otherwise, if the operation is update, then it does the same thing. It finds out the existing containers and the existing images that made those containers and sends the detail on from which container version number, as in from which tag of the image the container has been updated to which other tag of the image, so that you get a rich SMS elaborating what exactly happened within your cluster. It sends an SMS, and in both the create and update cases, it sends an OK object result back. So it just contains the UID, and true indicates that the request has been accepted. Don't need to add any messages here, even though you can if you want. The send SMS is a very simple function. All it does is it uses the payload that we get as part of the binding. It just adds the SMS message that you want to send in the collection. So the payload is actually a collection. So you just have to drop a message into the collection, and it would be processed by the binding itself. And that's.
I think here the summary is you can put your logic here, what you want to validate, what you want to check, and even talk with external system like Twilio. But what I see here is like a security thing. Sometimes you don't want to allow your cluster to talk with some like backend systems from your company. Mm-hmm. And this way you can just, only Azure Functions will be having access to these things.
Yes.
You don't have to give access to your whole cluster, to your namespace to access these. I think is a use case for that as well.
Yes, exactly. So if you want, you can put your functions in a VNet as well, and that way it will only be visible to your cluster. For this demo, I would just keeping it very simple right now.
Correct.
And yeah, I also want to show you something if I can here. So if you're using VS Code, then and you have this Azure extension involved, it's very easy to deploy a function in your subscription. After you create a function app, you'll see it listed within the subscription. You can just right-click it, and if you are already in a function project, then you can deploy it. Select deploy to function app, and your function app would be deployed right from here. And another thing is that your secrets actually live in a separate file, which is called local.settings.json. That's where it's not. It's also added in gitignore, so it doesn't get committed to your source control. But your actual settings live here. So in order to publish those as well to Azure, all you need to do is in the same extension, when you expand your Azure function, you would see a section called application settings. You just need to right click it and click on upload local settings. And that would take your local settings.json file and publish it along with the function to Azure. So I have already deployed this function to Azure, so I would quickly jump over to the reverse proxy part of it. So first, let me show you the structure. You can see that there's just one file in the reverse proxy, which is this main.go file. So what we are going to do is go through the source code of this program. So let me go back to presentation mode. And I will walk you through the structure step by step. So the first part is the configuration. So this configuration already has a bunch of default values in it. Of course, if you want to use the container image that I have already published, then you would need to override some of these configurations using environment variable. The most important one of them is the URL to the function app that you have. So right now I've made it point to the function app that I deployed. And it also, one of the requirements of the services that act as validating webhook is that they should be exposed over the scheme should be HTTPS, which is the transport channel should always be secured. In order to do that, you require two certificates. One is the public certificate that is used by your client, and the private one, which is used by the server. So you need to specify the path to the two certificates. And I will show you that you don't need to put these certificates in your application itself, because you would want to keep rotating those certificates from time to time. So they actually live as part of a volume, a secret volume that will mount, but I'll talk about it later. Apart from that, this is a simple listen on address. So this application is going to listen to on port 8080. So apart from that, let's jump onto the main method, which is this one. So here you can see that what I do is I process the configurations first, and then I create a new instance of the server, which I'll go to next. But essentially, once you get a server object, then you just add those certificates that I spoke about earlier to it. And that's how you end up having a server listening to the port that you specified using the certificates that you supplied. Let's talk about the bit that provisions the server. So it is very simple. We just need to listen to a single endpoint, which is the default endpoint. And what I did was I provisioned the part to the default endpoint, and I mapped it to a handler. And apart from that, the other configurations are just responsible for specifying the multiplexer and the address on which the server should listen to. So if you look at the handler, what it does is it simply takes in the request and the response writer, fairly standard Golang syntax for building applications that can listen to HTTP requests. It directs the request over to another function. And what this function does is it simply forwards the request to the Azure function, the URL of which we specified in the configuration. And it alters the name of the host, because the original request would be directed to this reverse proxy, but then you want to forward this request onto the URL of the Azure function. So fairly standard, just a handful bit of code, but all it does is whatever requests come to it, it would forward them onto the Azure function.
And that would be the glue between AKS control plane
Mm.
and the Azure Functions. As we don't have that connection at the moment, then we need that HIVS proxy just to make sure that we can connect there, and that's good.
Yes, exactly. That's what that is for. So I have built and published this particular application as an image in Docker Hub, which we'll refer to next. So let's walk through the specifications one by one now. Let's look at the specs. So the first part of the spec is the deployment. So the application, the reverse proxy application that we just now saw, is packaged and run available as an image in Docker Hub. But we need to deploy this as a service in our cluster so that our control plane can talk to this service. So for that, the first thing that we need to write is a deployment. Fairly standard syntax. You specify the name selector, set the replica count to 1 just for this demo, but you can obviously choose a much higher replica count. Let's look at the template. There's not much fancy here. This template is for the pods that would be created in your cluster. Here we are just specifying the name of the pod. Finally comes the spec part. Here we specify the name of the container and the image. So that's the image that I have published to Docker Hub. You can refer to it or build your own image and use that. Pull policy is to pull this image every time. So remember that our proxy listens on port 8080. So that's the port that we have specified here. It's a good practice to specify how much resource your cluster, your pod would be using. So that's the section that specifies that. So now comes the more interesting bit, that the certificates that that application requires. Remember that in the application code, we simply specified a path from where the pod should pick the required certificates. And this is how we mount a volume that contains those certificates so that it can be read by the pod. So I've specified the volume mount here, and the mount path that I've specified is the same path where the application is going to read the certificates from. Very interesting to see how that those certificates are provisioned at that path. So what you're right now seeing is the volume section. So here we are going to create a secret, and we are mounting that secret as a volume. So that secret already contains the certificates. I'm shortly going to talk about how you create secrets and how you create and how you provision the certificates in just a minute. But for now, just remember that this is how you can mount a secret as a volume. You just need to specify the name of the volume and the secret that needs to be mounted by specifying the name of the secret here.
And that's going to facilitate, this certificate rotation without having to change the.
So sort of. So you would still need to provision new certificates, but then you can simply put those new certificates in the existing secret, and that would get automatically picked up by your application. So there's no disk as such that contains your secrets, because secrets actually live in tempfs, which is you can think of it as the RAM, you can call it. So they are not persisted on the disk. So if you ever need to make changes to your secrets, just that data simply lives on the RAM, and that's from where it is read. So after you have built the deployment object, you just need to expose it via a service. Remember that service is a load balancer that can forward the traffic to any of the available pods. And this is how it is defined. You specify a name. Remember that we need to send traffic to port to an HTTPS endpoint. So that's what we have specified here, that it would receive requests at port 443, but then it would forward the request to port 8080 of the pod. So I think it's a good time right now to talk about how we generate the certificates. So that's something I will talk about next before I move on to the last bit of how you create a validating webhook configuration. So the first certificate that we need to provision is the CA certificate. So CA is the authority that signs your certificate and makes it valid. So here we are, since we are going to self-sign the certificate, we need to generate the CA certificate. Then we generate a key for generating our certificate. The next command in this script generates the actual certificate and also signs it using the CA certificate that we created. So one of the key things that we need to remember while provisioning this certificate is that the common name of the certificate, as in for the name of the party for the service for which the certificate is valid, is the name of your service, the names dot the namespace of your service and dot svc. So because unless your service presents a certificate with a valid common name to the validating webhook configuration, it won't accept it. So you need to be a little more careful when you write the common name here. Finally, what another command that I wrote here is what it would do is it will create a base 64 encoded CA certificate. So Kubernetes doesn't understand the native text. So if you're creating a secret, it should be base 64 encoded. So what we are doing here is we are taking the CA certificate and converting it to base 64 format. Yep. What this line of code does is that it would remove new line characters from the base 64 encoded certificate and will use this value in our validating webhook configuration, which we'll talk about in just a minute. So once these certificates are in place, what I did is to create a secret. It's a generic secret, and what it is going from where I'm feeding it value is from the certificates that I created. So I generated the public certificate for the public certificate that we generated through the script in the file called cert.pem. So that's from where the secret will be read. And another part of this secret is the key, which would again be used by the application that we just spoke about. And that would be read from the file key.pen. So when you specify, when you're reading values from a file, you don't need to base 64 encode them. It's done automatically by Kubernetes. But if you're storing, storing values that need to be used by Kubernetes somewhere else, you would need to base 64 encode them yourself. An example of which is the base 64 encoded CA certificate that we generated. We are going to use that value in its base 64 encoded format when we provision the webhook. So now that we have seen how certificate is provisioned and how it is mounted to our pod, let's go back to our deployment spec. And I will like to draw your attention to the last part of this spec, which is the validating webhook configuration. So this is what adds an admission controller to the existing API server pipeline that we saw in the architecture before. So you specify a configuration of type validating webhook configuration. You can give it a name, and this needs to be of type webhook. So in fact, webhooks are the only types of webhook configurations supported, which don't live inside the cluster. Sorry, not exactly inside the cluster, but for which there are services, either services running within the cluster or they are an out of cluster service, for example, Azure Function that lives totally outside the cluster. Here we are going to direct the request to our Golang reverse proxy. So that's what we're going to tie this configuration with. So here you specify the name of the webhook, and in this section, you will see that this is a little different from the configuration that we saw in the slide, where we were sending the request straight over to our Azure function. Instead of doing that, what we are saying is that any validation request should come to a service, which is this service that lives in the default namespace and the path. So in the while we were talking about reverse proxy, I told you that we are only listening to one endpoint, which is the default path on in the reverse proxy, and that's what I've specified over here. The port number needs to be 443. In this property, looks quite big. Here is where you specify the encoded CS certificate. So remember that in the previous script that we went through, we encoded the CS certificate into base64 format, and we removed new line characters from it. So you need to take that value and paste it here, the one without new line characters in it. So how this whole thing works is that the API server would forward the request that it builds for validating a spec. It will send that request over to your webhook, your custom admission controller, and when it responds, it would, since it is running over port 443 or HTTPS, is using the HTTPS scheme, it would respond with a certificate, and that certificate is validated with this certificate that you specify over here. If you don't specify a certificate here, then that certificate needs to be known to the Kubernetes API server, because then it would use the default certificate chain that it has in order to validate the certificate. But remember that we generated a self-signed CS certificate, and it won't be available to the API server by default. That's why we have to put this value here. The rest of the rules remain the same. So when you create any new deployment within a certain namespace, if you issue a create or update command to it, then this rule would come into effect, and the rest of the paths remain the same. There is a timeout policy, the default policy. So if let's say this webhook fails to respond within 30 seconds, then the default policy is to fail the deployment, then to let it pass.
I think in summary here, you're deploying the reverse proxy that will be called by this admission controller. Yes. And this admission controller is running on the control plane of Kubernetes. And you have to give the public certificate for them to establish the TLS connection with your reverse proxy. And once that's established, then the reverse proxy is going to talk with the Azure Functions that's outside the cluster. And that's the whole beauty of this presentation, is how you move that outside the cluster. And that reverse proxy is going to do that glue. And normally in your example here, you're doing for create and update deployments. Every time that you try to deploy something, and they're going to run this code. That's very neat. Thank you for building that.
That's correct. Thanks. So yes, that's pretty much that we need to do. So in interest of time, I have already run the spec on my cluster. So now that everything is set up, what I'm going to do is issue a sample request to the Kubernetes to the AKS cluster that we have created, and using the native Twilio binding, we'll see some SMS coming our way to notify us whether deployment succeeds or fails. So in order to do that, I'm going to use the wonderful Your Phone app from Microsoft, which I use frequently on my system in order to stay connected with my phone. And the spec that I'm going to use, the spec does is it creates a namespace, and it tries to create a deployment in the namespace. And I can change the count of the replicas in order to trigger a failure or success. And it tries to deploy an Alpine image. So what we are going to do is first, let's try to run an invalid scenario. So I've reduced the replica count to 2. Remember that in our application code for Azure Function, we have written that don't allow any deployments to go through if the count of replicas is less than 3. So I'm going to save this, and then what I'm going to do is apply this spec. Spec is the name of this file. I press enter. See that the namespace got created, but our Azure function and hence our admission controller returned a message back to us asking us to create more than 2 replicas for this function.
That was pretty quick. That was very fast.
Yes, power of cloud.
Yeah.
So I have received an SMS as well. I think this is it. So here you can see that I received a message from Twilio. Let me. So that from Twilio trial account, and sent me the same message here that is trying to deploy something with lesser than the desired replicas, and that's why this deployment failed. So let's fix this issue.
That's great, by the way. That's great and very quick, and even SMS, everything works very neat.
So this time the deployment should succeed because I've increased the count of the replicas. So, and reapply this file. And this time you can see that since we met all of the conditions that we specified in the Azure function, it has now accepted the deployment, and I should receive the SMS now. So now you can see that I received another SMS from Twilio, and this time it says that the deployment did succeed. And you can think how useful it can be for SRE or ops team who always need to be in the loop of when new deployments happen, when things in your cluster change. So if this phone number is provisioned for an ops or SRE team, forgot to zoom in.
That's very handy, how even like in 2 minutes you deploy twice using custom admission controller and sending SMS, and that's a new times. If people watching these never did like cloud native development before, you should go and look on that, because to do that real life sometimes takes a long time.
Yes, exactly.
No.
There's one more scenario that I'm going to cover, which is to update the deployment. So there is another SMS that you should get. So in order to do that, what I'm going to do is change the tag of the Alpine image. And what I'm going to do is deploy this spec again. So we'll see that this time the deployment has been updated. And it went through successfully because it meets all the success criteria that we have defined in our function. Yeah, so now when we go back to our Yo-phone app, you would see that we have received another SMS from Twilio indicating that the update succeeded. And you can see because we collected the names of the containers that were part of the deployment from our spec, we were able to dispatch a rich SMS that would be useful to the ops or SRE teams. This SMS actually says the version of the deployment, which was the earlier version of the deployment and what it has been changed to. So these were the three scenarios that we had put in our Azure function, but you can obviously make it as complex or as easy you want. And this concludes my demo. You can read more about it on my blog, which is also cross-posted to Azure Tab. So you can refer to either of the two resources in order to read more about this application and its use cases. Thank you.
Well, thank you, Ro. So I have all the code. I can try to deploy it myself to learn more. It's following
Yes.
your article. Oh, how good, Ro. Thank you very much for that.
Yeah, thanks, Raul. It was great. And if you want to follow us and follow Raul, always the cloudblog.net. We put the links here on the description for. He's going to write a blog about this video as well, and you can follow us on Twitter and on azureta.com. And please subscribe to the channel. Thank you, guys.
Thank you, guys.
Bye bye.
Bye.